Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi again, everyone. Welcome to the continuation of the lecture for the course SMJE 3153 Control Systems. And for this video, I will talk about a new topic called Root Locus. So basically, in this video, I will talk about the introduction of Root Locus. What is it all about? Before looking at how to sketch the root locus, we will review some concept of vector representation of complex numbers. And then we will look at the properties of the root locus. And then we will look at the basic rules, how to sketch the root locus before looking at an example. Okay, let's look at the situation here. We have a open loop system transfer function given as shown here, and okay, we have a second order system and we have two poles. You can see one is at for the open loop, we have one at s equals to 0 and another one at s equals to minus 10. So the system is stable in the open loop. But what happens if we apply a negative unity feedback to the system and we have a gain k, and we want to look at what happens if we change the gain from 0 to increase it to a bigger value. So if you do some numerical computation, this is what's going to happen if you increase the gain k. Okay, this is column. This table shows the value of k as we change from 0 all the way to 40 and so on. And you can see that the closed loop poles, so these are the closed loop poles, okay, it changes from, you can see that the values changes from being real until it becomes imaginary. And basically the closed loop poles are moving as shown in this bottom left half part of this screen. You can see it moves. And as a result of changing the gain k, you can also see that the step response also changed. You can see the, for example, the rise time or changes. Okay, the time constant is changing. It changed from being over dam all the way to critically dam and then becoming under dam. Right now you can see you have an overshoot here. So we want to analyze this kind of situation and see if we can generalize for the negative unity feedback. Actually, for a feedback system, how we can visualize the movement of the poles as we vary a gain k. Okay, so let's review the vector representation of a complex number. Assume we have a function fs equals to s plus a, and we have a complex number s1 equals to sigma plus j omega. So how do we draw this in the complex plane? So we can use the real and imaginary part, sigma plus omega. But that same number can also be represented by the magnitude and phase. Okay. So what happens if we substitute this value into the function? So as a result, we will get another complex number. So now the real part has changed from sigma into sigma plus a, and then the imaginary part is the same. So again, you can see that we can use a vector to represent the resulting complex number. If we look at the function, okay, we can see that the function is s plus a, so we can say that the a is a 0, okay, using the previous definition that we used, definition of complex function consisting of zeros and poles. As you can see that if you shift the original vector as much as a amount to the left, okay, a is the 0, we will see that the only thing that is changing is the initial point of the vector. So what we can see is we can represent the complex number fs as a vector drawn from the 0 of f. Okay, so you can see that there, and if we have fs equals to s plus 7 and we want to see the value of the resulting complex number if, for an s equals to 5 plus j2, so all you need to do is to identify the 0, which is minus 7, and you can just draw the vector, okay, from the 0 of f into the complex number 5 plus j2. Okay, so this is just a review of vector representation of a complex number. Okay, now let us apply the concepts to a more complicated function. So as shown here, assuming we have a function f where the function consisting of a product of several zeros as shown here. So the numerator are the zeros, and in the denominator you have several poles, product of several poles. So this is the typical transfer function that we saw earlier. So each factor in the numerator and each factor in the denominator is a complex number that can be represented by a vector. So as shown before, so just one of these is consisting of a vector. So the function defines the complex arithmetic to be performed in order to evaluate fs at any point s. Okay, so since each complex factor can be thought of as a vector, hence then the magnitude of fs at any point, so the magnitude is represented by m, so it's given by the magnitude of the multiplication or the product of the magnitude of the individual vectors for the zeros divided by the magnitude for the individual vectors of poles. Okay, so that will be the magnitude of the overall resulting function if you substitute a complex number s. So similarly, the angle of the resulting vector is given by the angle of the individual vector. Like for example, in this one is the angle of a 0 vector to the particular point, okay, drawn positively, okay, from the real axis. Okay, you have to sum all the angles of the zeros, okay, into that particular point, minus all the angles of the poles to that particular point, again taken from the counterclockwise direction positively. So to illustrate this, assuming we have a function fs equals to s plus 1 over s plus 2, so if we want to find the function fs at this particular point, all we need to do is we identify this point minus 3 plus j4, so as shown here, minus 3 plus j4, and then we can draw that we have 1 0 and 2 poles. So you can see we have 1 0 at minus 1 and 2 poles at 0 and minus 2. So if you draw these vectors, okay, the goal is just to evaluate f at that particular point. If we do that, then we find the magnitude and phase or the angle of the individual vectors to this particular point, and you will see that as a result, the magnitude of the overall resulting f will be as shown here. So first of all, let's look at how we find the magnitude for this particular vector. It is just the you can see that for this particular point minus 3 plus j4, then you can find this length here is using Pythagorean theorem, okay, 3 squared plus 4 squared, which is the square root of n. Use the square root and you will get that the magnitude of this particular vector to be 5, and then this angle can also be found, which is equal to 180 degrees minus this angle, which is the arctangent of 4 over 3, and you will get 126.9. So that's the angle, that's the magnitude and angle of the first vector. So if you use the relationship shown in the previous slide, then the magnitude will be the magnitude of the zeros, which is square root of 20, which is this vector, divided by the magnitude of the vector from the poles to that particular point, which is 5 and root 17. Whereas the angle is the angle made by the 0 minus the angle made by the vectors representing the poles. and then the result will be 0.217 angle minus 114.3. So in general, we will use this relationship later on when we want to sketch the root locus. Okay, next, let's look at the general closed loop system as shown here. So you have the open loop transfer function KGS, and then you have a feedback HS. So if you write the expression for the closed loop transfer function, it will be given by this expression kg over 1 plus kg h. Now, because we are interested in the poles, okay, we want to see how it moves as k is varied. So the pole S exists when, okay, so when 1 plus kgh equals to 0. So this is the denominator for the closed loop transfer function, and we call this the characteristic equation. So interestingly, this is the condition, okay, for a pole to occur, that the pole S will cause this denominator to be 0. So we can rewrite this equation kgh equals to minus 1. Now this minus 1 can be represented in vector and angle form. So minus 1 is just 1, the magnitude is 1, with an angle of odd multiplicities of 180 degrees. So if k is 0, so 180 degrees from, if you count 180 degrees in the complex plane counterclockwise, then you will see it's exactly at minus 1. So if you look at this expression, then you can say that that means in order for the S is a pole, then the magnitude should be 1 and the angle should be odd multiples of 180 degrees. Okay, in conclusion, S is a pole if the resulting complex number satisfies the angle criterion above and K satisfies the magnitude 1 over G times H. So let's look at again this situation just to check our derivation just now. For this particular system, okay, the closed loop transfer function is given by ds equals to k over s squared plus 10s plus k, and we have obtained some values of that particular transfer function. So you can see the poles are moving along a certain path. That's the locus basically. So you can see that you can check that if you choose any pole here, given the amount of k, then the expression in the denominator should be 0, okay, based on our derivation just now. So for example, if we choose k is equals to 25, then if you substitute 25 and s is equals to minus 5 into the denominator, you will see that it becomes 0 for that particular set of values. So you can verify that this works for other points too. Okay, let's just reiterate the derivation just now, just using a different example. So now we have the kgh equals to ks plus 3s plus 4, and we have poles minus 1, minus 2 as shown here. So basically, the relationship that we have derived, it informs us that if you have a point, okay, say in the complex plane, say anywhere, but assuming this is the particular point, so that point will be in the locus, okay, in the root locus of the closed loop system, if the angle made by the vector of zeros, so these are the vector of zeros, if the angle theta z1 and theta z2, if this angle minus the angle made by the vector of poles to that particular point, so here theta p1 and theta p2, so if this angle minus this angle equals to a multiple of 180 degrees, then that particular point that we have selected is indeed on the root locus. Okay, so once we have identified that that particular point is on the root locus, then we can use the value of the of that particular real number, real and imaginary part of that particular point to find or to solve for k. Okay, so first we identify the point, ensure that it's on the locus first using the angle criterion, and then we can solve for k to find the k that actually give this particular point. In this case, the pole is minus 3.23 and plus 0.464i, and the gain that give this particular point will be 6.44. So basically what I have just mentioned is shown here in this equation, where the angle made by the vector of zeros, this angle minus the angle made by the vector of poles, theta p1, theta p2, the sum should be, this total value should be the multiple of 180 degrees. Okay, if this is satisfied, then that means the particular complex point is indeed in the root locus. Then we can solve for the k by using that particular point value. If you substitute it into the g and h, you can solve for k. Okay, now we look at some basic rules of how to sketch the root locus. So the first rule is how many branches are there for the locus. So the locus of the roots of the characteristic equation, i.e. the root locus. Okay, this is the characteristic equation. So it will begin at the pole of the open loop transfer function. Okay, so just that's the strength of the root locus, by the way. You don't really need to solve for the closed loop. Just by looking at the open loop transfer function, then you can identify the behavior of the closed loop poles. So basically, if we can identify the poles of GH, then that means we already know the number of branch. Okay, so for example, in this case, this is the example we saw before in the introduction slide, that we have just two poles. That means we have two branches. So in MATLAB, conveniently use different color for different branches. So you have green and blue in this case. So in another example here, we have the poles of the characteristic equation. Okay, 3 poles, and you can see then there should be 3 branches, right? So essentially you can see this is another advantage why we study root locus. You can see that this pole is in the right half plane, so it's in an unstable system initially. So by choosing the correct value of k, you can move this pole from the right half plane to the left half plane, so making the system stable. So but of course you have to find the appropriate value of k to move the system from unstable to become stable. Okay, that's the interesting fact about the root locus. Number two is the symmetry. So the root locus is always symmetrical about the real axis. So this is the real axis. You can see it's symmetrical. It's the mirror image on the top part and the bottom part, and vice versa. Okay, so so the number of branches depends on the number of poles of the characteristic equation, and then it's symmetry. That's the first two rules. And on the real axis, for k larger than 0, the root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop 0. So if you can, after you have plotted the poles and of course zeros, you will see in the real axis that the existence of the locus or the branch should be on the left of an odd number of real axis poles. So you can see in this part this part is to the left of a pole. Here we have one pole, so odd. One is odd, so you have the locus here. But over here you don't have any locus because to the right here is 2, so that's even. So you have 2 poles, so there will be no locus here. So same thing here. There's no locus here, because there are 2 poles and, well, 2 poles and zeros, altogether 4. But over here, if you count, there's odd number of poles and zeros, so it should be, the path should be, the locus should be here. And then the starting and ending points, the root locus begins at the finite and infinite poles of G, H, and ends at the finite and infinite zeros. So for example, if you have this system and you have 2 poles and 2 zeros, so if you plot this in the complex plane, then the locus will start at the pole. So these are the 2 poles, so somehow it will start at the pole. But where are the location of the branch of the locus in the real axis, as using the previous rule? So only on the left of the odd number of poles. So over here there will be no locus. Over here you have 1 here, so there should be some locus here. Okay, here there's 2 poles on the right, so there shouldn't be anyone. But over here there are odd number of poles and zeros, 1, 2, 3, so there should be some locus here, and over here no. So you know initially that there should be some locus, the movement of poles and zero, the movement of poles will be in the real axis will be somewhere here and somewhere here. So as shown here, so you can see, okay, the green, okay, the pole at -1 moving from here, ending to a pole, ending to a 0, whereas this one ends to another 0. Okay, so it will always move from pole to a 0, where the real 0 here in this case, when k is big, then it will end at that particular 0, but in some cases the 0 will be at infinity. Then we have to identify the asymptote. That's the 5th rule, by the way. If we have a pole 0 at infinity, then the root locus approaches the straight line as asymptotes as the locus approaches infinity. So how do we know, how do we define the asymptotes? Okay, asymptotes are just straight line. So let's define the sigma A as the asymptote real axis intercept, and theta A as the angle of the asymptote. So basically we can define the real axis intercept sigma A and theta A as follows, as shown here. Okay, where sigma A is equals to the value of the pole minus the sum of the value of the zeros divided by the total number of pole minus zeros. And same thing here, the angle will be the odd multiples of phi divided by the difference between the number of poles minus the number of zeros. So for example here, by asymptote we are talking about this straight line. Okay, so we will look at an example later on. By the way, the definition is in the text. If you want to refer to the text, you can do so later on, but over here we just focus on how to sketch the root locus. So as an example, let's look at this function where the system we have 1, 0 and 4 poles. Okay, so first of all, how to sketch this the root locus? So first of all we just draw the zeros and poles as shown here. Okay, so we have label the poles as x and 0 as circle. So rule number 1 is number of branches, so we have 4 poles, so we have 4 branches. That's easy. And it's symmetrical, so that's rule number 2 is symmetry in the real axis. Again, it's just a mirror image. And then rule number 3 says that the existence of the locus in the real axis will be depending on the number of odd number of poles and zeros. So here I've labeled in this case you have 1, so there should be a path there should be a locus here. In here, there should be no locus here because it's just 2. Here there are 3. Here there are 4. So you can initially identify the location for the locus. Okay, so 4 poles, so 4 branches. So there should be 1, 2, 3, 4 branches. Okay. So the fourth rule says that the path will move from pole to 0. So we already indicate here. But over here, the zeros will be at infinity. Okay, as shown here. So we need to find the asymptote. So if we use the rule given before, so the asymptotes, the poles are 0, okay, 1, 0, minus 1, minus 2, minus 4. So you minus the 1, 0 at minus 3, divided the total number of poles are 4, minus 1, 0. Then you will get this to be minus 1.33. So that will be the intercept of the asymptote at the real axis. Okay, so you can mark that point. And then you need to find the angle of the asymptote. So if you use the equation, it's cannot be seen here, the equation in the previous slide. Then you will see that the angles will be, this is the first one, 60 degrees. And then the next one will be, if I'm not mistaken, 180 degrees. And then 300 degrees. Okay, you substitute k equal to 0, 1, and 2. So you will see this is the first asymptote. I've drawn that, which is angle of 60 degrees. And the second one here, 180 degrees. And the third one, 300 degrees. So these are the asymptotes. Then that means that the locus, okay, the root locus will approach the asymptote as k approaches infinity. Okay, the first one is not really correct. It should be closer to the asymptote. This one is correct. Okay, so that is the resulting sketch of our root locus just by using the 5 rules, 5 fundamental rules. Okay, so in the next topic we will see more rules in order to refine our root locus. So for example, the point where the locus leave the x-axis, leave the real axis can also be found. Here is just a sketch. And the point where the locus intercept the imaginary axis can also be found. That we will do in the class. So here I've put it at J2. But if you look at the real locus using MATLAB, okay, you can see it's actually at 1 something. Okay, so this can be found using other rules to refine the sketch of the root locus. Okay, I think that's all for this video. These are the references that I use. You can refer to the text for the derivation of the formulas and so on. We will go into more detail in class later. So thank you for your attention. See you in class. Assalamualaikum warahmatullahi wabarakatuh. Bye bye.